In this lesson, we're going to learn about something called radicals. So we're going to explain what radicals mean, and then we're going to learn how to simplify them to lowest terms. And we're also going to multiply, divide, add, and subtract radical expressions. We're going to save rationalizing the denominator till another lesson. So first, what the heck is a radical? Well, radical is just a fancy way of saying root. So it's just an expression that has a root in it. So this is a radical. This is a radical where there's an expression underneath there. So let's go back into a quick understanding of what we know about roots already. So if I were to ask you for this, what would you say? What would you call this? You call this the square root of 9. Where do we get the squared from? There's always been a tiny little 2 here. Every time that we've seen a root that looks like this, we've actually always assumed that there was a little invisible 2 there, and that's why we've said the square root. And so when we're looking for the square root of 9, we're looking for a number multiplied by itself 2 times makes 9, and that would of course be 3. It could be negative 3 as well, but because this root was given to us and wasn't a plus or minus, I'm just going to assume that it's looking for the positive root. So we know 3 works because 3 multiplied by itself, 3 times 3 makes 9. So 3 2 times makes 9. So we take a look at this one. This is another radical, and maybe we've never seen this before, but here there's a little 3. Normally that's just blank, but what we just realized is that actually there was a 2 there every time that it was blank, which is why we called it a square root. So because this is a 3, this is called a cubed root. And so this question is asking for the cubed root of 27. So what that means is what number multiplied by itself 3 times makes 27? Well, if we take 3 and we do 3 times 3 times 3, 3 times 3 is 9, times another 3 is 27. So that means that the cubed root of 27 is just equal to 3. So now we know a little bit more about different types of roots that we could be working with. Cubed root, you could be dealing with 4th root, 5th root, etc. Radicals could also take on a few forms. So sometimes a radical could look like this, and sometimes a radical could look like this. So this is called an entire radical. So the coefficient is 1, there's an invisible 1 right there, and the number completely exists under this root. And over here, this is a mixed radical. So this means 3 root 5 means 3 root 5s, or another way to think about it is 3 times root 5. That's what that means. So in this lesson, we're going to learn how to simplify radicals. And sometimes radicals are simplified. When they're simplified, they look like this. They look like an entire radical. Or sometimes they look like a combination of a number times a radical, and that's its simplest form. So in order to simplify these guys, we just need to know 2 rules and only 2 rules. So they're laws of radicals. One is the multiplication rule and the other is the division rule. So what the multiplication rule says is if we have an entire radical, like this guy, and we're able to break up whatever's underneath this root sign into 2 factors, that's just going to be equal to the square root of the first factor times the square root of the second factor. So I'll give you an example. We can break up the square root of 24 into 2 factors. So we could break it up into 2 times 12, or we could break it up into 6 times 4. Let's just pick 6 times 4. So if 24 is the same thing as 6 times 4, then the root of 24 is the same thing as the root of 6 times 4. And what the multiplication rule says is that that's equal to the root of 6 times the root of 4. So we're allowed to break up a radical into its factors, each under individual root signs. So let's use this rule to simplify some radicals on the next page. So this first example asks us to simplify these guys. So by simplify, I do not mean punch this into your calculator. Punching this into our calculator is going to give us a decimal, and that's not what we're looking for. We're looking to rewrite this in so that the number stays exactly the same, or the value stays exactly the same, but it's as simple as possible. Just as similar to if I asked you to simplify the fraction 4 over 6, we would simplify it by dividing by 2 on the top and dividing by 2 on the bottom, and we would leave it 2 over 3. They're totally equivalent, but this is considered a simplified form of this fraction. So what we're going to do to simplify a radical is we're going to look to break this 75 up into 2 or more factors that we could take the perfect square root of, at least one of them. So here's what I mean. First of all, we need to agree that this is asking for the square root of 75. We know there's a little 2 there. So is there a factor of 75 that we could take the square root of and it give us a nice number? So if we're looking for a perfect square. So let's just write out some perfect squares to give ourselves an idea. So 1 squared is 1. So 1 is a perfect square. 2 squared is 4. So 4 is a perfect square. By perfect square, I mean we can take the square root of 4 and get a nice even number, an integer, 2. 3 times 3 is 9. 9 is a perfect square. 4 times 4 is 16. 5 times 5 is 25. 6 times 6 is 36. 7 times 7 is 49. 8 times 8 is 64. 9 times 9 is 81. 10 times 10 is 100. 11 times 11 is 121. And 12 times 12 is 144. Those are all that we need for now. So because of the multiplication rule, it says that we can break this guy up into its factors and take the square root of each of them. It makes sense to break up 75 into a factor that is a perfect square, because then we can take the square root of it. So let's go through these numbers and figure out which of these numbers goes into 75. Obviously 1 is a factor of any number, but if you take the square root of 1, it just gives you 1. It's not going to change the 75. 4 is not a factor of 75, either is 9, either is 16, but 25 is. So we can break 75 up into lots of different factors, but it makes sense to break it up into a perfect square. It makes sense to break it up into 25 times 3. And the reason why this works out is because that multiplication rule that we just learned on our first sheet, we can break this up into the square root of 25 times the square root of 3. And what is the square root of 25? Well, that's a really nice number. It's just 5. And what's the square root of 3? Not a nice number, so you're just going to leave it alone. So if our calculation is correct, if we were to take the square root of 75 and press equals on our calculator, that should be exactly the same thing as saying 5 times the square root of 3 and pressing equals on our calculator. So try it now just to make sure. Prove to yourself that 5 times the square root of 3 is the same thing as the root of 75. So if you've done it and you've agreed, yes, they are the same thing, we have simplified this. So we know we've simplified this because we're going to go over to the right and take a look at a quick checklist to help us give us an idea of when we have simplified it. So a radical is in its absolute simplest form if it has all the following. So the radicand. The radicand is whatever lives underneath the square root, or whatever the root is that we're working with. Right now we're working with square roots. So the radicand, so this guy right here, has no more perfect square factors other than 1. So taking a look at this 3, sometimes we got to break up a radical multiple times, but taking a look at this 3, is there any more perfect squares that go into this 3? Nope. 1 of course goes in, but that's not going to help us get rid of the 3. 4 is too big. So we're done. The radicand does not contain a fraction. We haven't dealt with fractions yet. And no radical appears in the denominator of the fraction. We have no fraction, so there can't be a denominator. So we're done. So let's try B. Let's go ahead and do the same thing with the root of 24. So let's see if there's a perfect square. And again, I'm looking with perfect squares since I have a square root. So something I can take the square root of. I want to see if there's any factors of those of 24 that are those numbers. So I can break 24 up into 2 and 12, but can I take the square root of 2? No. Well, I could, but it's going to be an ugly decimal. Can I take the square root of 12? Is that a nice number? No. So it doesn't make sense to break it up into 2 and 12. What are some perfect square factors of 24? Well, we have 4. 9 is not a factor. 16 is too big. So the biggest perfect square factor of 24 is 4. So let's break this guy up into the square root of 4 times 6. I always like to write the one that I know is going to simplify first. You don't have to do that, but because it's going to be the coefficient anyways, it makes sense. So we know that from the multiplication law, we can break this up into the square root of 4 times the square root of 6. And we know the square root of 4 is just 2, and the square root of 6 is just root 6. By the way, notice I'm not taking the positive, I'm not saying plus or minus 2. The reason is because this square root was already given to us in this problem, and there's no plus or minus. We didn't have to create the square root, so we're just going to leave it positive 2. If there was a plus or minus there, this would be plus or minus 2 root 6. So let's make sure that we are totally done. 6, is there any perfect square factors of 6? The answer is no, so we are completely done. To triple check, we got extra time on a test. Make sure that we have broken this up correctly. We would check what the square root of 24 is, press equals in our calculator, and then we would check 2 times the square root of 6, press equals in our calculator. If you're getting the hang of this, try these on your own and then just come back to the video just to check to make sure that you got the same answer. If you're still having trouble and you need some more help, stay with me. Let's break this guy up here. So this is 5 times the square root of 27. So we're trying to simplify this guy. So 5 is already simplified, so I'm just going to leave 5 alone. And I'm going to see if I can break up 27 into any factors that are perfect squares. So going through our list, I can see that 9 or 27 is divisible by 9. So 9 is a factor, and 9 is also a perfect square. So we can break up the root of 27 into the root of 9 times 3. So I'm going to leave that 5 alone. I'm going to break this guy up into the root of 9 times the root of 3. And I know that I'm going to leave this 5 alone, and that the square root of 9 is 3. And I'm going to put that in brackets because I know the 5 is multiplying against these other terms, or these other expressions. And then what does the square root of 3 simplify to? Nothing. It's as simple as it can get. There's no perfect square factors of 3, so we're going to leave this alone. Our final simplified form, we can multiply 5 and 3 together, and that's going to make 15 root 3. So to make sure that we've got it right, we would check in our calculators what's 5 times the square root of 27, press equals, and make sure it's the same thing as saying 15 times the square root of 3, which it is. So for the last one, try this guy. Try to look for a perfect square factor of 22, and then come back to the video once you think you've got the answer. So if you're back, you would have tried a whole bunch of perfect square factors. 22, the only factors of 22 are 1 and 22 and 2 and 11. And 2 and 11, none of those are, other than 1, are perfect square factor. So this can't be simplified further. These next examples ask us to do something a little bit different. It asks us to convert these mixed radicals into entire radicals. So a mixed radical has a coefficient other than 1 multiplied by some sort of radical. So it's looking for us to go backwards, back to like changing this into 45, the root of 45, for example, where the coefficient is 1. So can we convert this guy into an entire radical? So we're not going to change the root 5, but we definitely got to change the 4. That's the problem. So what could I change 4 to so that it's equivalent to the root of something? So I'll leave the root 5 alone. What could I change 4 to? Well, isn't the root of 16 the same thing as 4? So aren't those two the same? So I haven't these are totally equivalent. And now I just got to do one final step to make this an entire radical. I'm going to change this to the root of 16 times 5. So this is the multiplication rule that we talked about from the very first page of this lesson. I can change this guy. The root of 16 times the root of 5 is the same as the root of 16 times 5. And then I can finish this off as, what's 16 times 5? Well, it's just 80. So the root of 80 has to be the same thing as 4 times the root of 5. So just like we've gone backwards. And now we've made this into an entire radical. So let's try the next guy. 3 root 10. So I'm not gonna change the root 10. That's already a radical. But what could I change 3 to? Well, that's the same thing as the root of 9. So I can rewrite this as the root of 9 times the root of 10 is just going to be the root of 9 times 10. And the root of 9 times 10 is the root of 90. And so if I check in a calculator, 3 times the root of 10 press equals, and then check what the root of 90 is. It should equal exactly the same thing. Let's try this last guy. So I want to make this into an entire radical. So I'm going to leave the root 3 alone. And is there any root that I can make that would be the equivalent of -6? So the square root of what would make -6? Square root of nothing would make -6. The square root of 36 would be 6. So we're just going to leave this negative on the outside here. So I have negative the root of 36 times the root of 3 should be the same thing as this guy. So let's keep simplifying. If this is true, then this should be equal to negative the root of 36 times 3. And we know that 36 times 3 is just 108. So these two expressions must be equivalent. Negative 1 times the square root of 108 has to be the same as -6 times root 3. All right, so you know everything there is to know about multiplying using the multiplication rule. So you should be able to figure out these next questions on your own, but I'm here to help you if you need it. So the next questions just give us some multiplication questions and just says to simplify. So let's just keep using what we know about radicals and let's simplify these guys. So this is asking us for the root of 2 times the root of 10. So sometimes it makes sense to go into each of these individual radicals and try to simplify them individually, but if we can condense it into one first, sometimes that's more helpful. So I think the easiest thing to do here is change this into the square root of 2 times the square root of 10. We know it's the same thing, it's just the square root of 2 times 10. And then we know that that's just the same as the square root of 20. And now we can look at that square root of 20 and ask ourselves, is that totally simplified? So the previous question we didn't simplify because it didn't ask us to. It just asked us to change it into an entire radical. So now this is an entire radical, but we've got to simplify. So are there any perfect squares inside the root of 20? Well, isn't 4 times 5 equal to 20? And we can change the square root of 4 into 2. And the square root of 5 is just the square root of 5. And we are done. So the root of 2 times the root of 10, press equals in your calculator. It's got to be the same thing as 2 times root 5. Let's go slightly harder. What to do with this guy? You know everything you need to know to be able to deal with this. What does -2 root 5 mean? That just means -2 times root 5. And then we have times. What does 3 root 10 mean? It means times 3 times root 10. So these are all just multiplying against each other. And which one of these can be multiplied? Well, -2 times 3, that's just going to make 6. So I can simplify this guy times this guy. That's just going to make -6. And I know I can deal with this root 5 times this root 10. That's just going to be the root of 5 times 10. And I can keep simplifying this to the root of 5 times 10, which is root of 50. And then before I finish, I got to make sure that there's no perfect squares inside that 50. So is there? Doesn't 25 go into 50? So we can break up this root of 50 into 25 times 2, the root of 25 times 2. And the root of 25, that's just going to be 5. And the root of 2, we're just going to leave as the root of 2. So let's finish this off as this is going to be -6. The root of 25, that's just 5 times the root of 2. We know we can simplify these two numbers here. So we have -30 times the root of 2. So if our calculations are correct, -2 times root 5 times 3 times root 10 should give us the same thing as -30 times root 2. And we're done. Now let's try an example that looks like this. So now we've got some addition in here. So this is 2 root 2 times all of this. So we got to times this 2 root 2 times the roots of 7. And then we got to times this 2 root 2 times 3 root 3. So we have to expand this guy. We've got to multiply this 2 root 2 times everything in this bracket. And there's two different terms in this bracket. So I'm going to rewrite this as 2 root 2. And then we've got to times it by 7. Root 7, sorry. Plus, then we got to do 2 root 2 times 3 root 3. So again, I just did 2 root 2 times the root of 7, boom. And then 2 root 2 times 3 root 3, there we go. And so we know how to deal with this. What can we multiply here? This is just 2 times root 2 times root 7. So we can multiply the root 2 times root 7 into the root of 2 times 7. Plus, how about this guy here? This is 2 times root 2 times 3 times root 3, just like the previous example. So what can multiply together here? Well, we can do the 2 times the 3, and then we can do the root 2 times the root 3. So we know 2 times 3 is just 6, and then we can change this into the square root of 2 times the square root of 3, which is square root of 2 times 3. Let's keep on finishing this. So we've got 2 times the root of 14 plus 6 times the root of 2 times 3 is 6. So before we finish, are there any perfect squares within 14? The only factors of 14 are 1 and 14 and 2 and 7, and none of those are perfect squares. How about in 6? Are any perfect squares in 6? The factors of 6 are 1 and 6 and 2 and 3, and none of them are perfect squares. On top of that, we cannot add these things because this is saying there's 2 root 14s plus 6 root 6s. This is equivalent of saying like there's 2, let's say x's and 6 another thing, 6 y's. Those are not common, those are not like terms, so we can't add them. So we are totally done. All right, can we take it one step further here? So we have these two terms, 3 and negative 2 root 6 times these other two terms. We have 2 plus 3 root 24. So we got to take every term in this bracket and multiply by every term in this bracket. And we know how to do that. We're just going to FOIL. We're going to do 3 times 2, and then we're going to do 3 times 3 root 24. Then we're going to do the same thing with the negative 2 root 6. We're going to multiply by 2, and then we're going to multiply by 3 root 24. So let's do it. So first I'm going to take the 3 and multiply by the 2. That's easy peasy. And then I'm going to take the 3 and multiply it by the 3 root 24. And then I'm going to take this negative 2 root 6 and times it by 2. So I'm going to take negative 2 root 6 and times it by 2. And then I'm going to take the negative 2 root 6 and times it by 3 root 24. All right, so let's finish this off. Let's do the first guy first. The first term is 3 times 2. That one's easy. That's just 6. Plus, let's take a look at the second guy. I have 3 times root 3 times root 24. And I know 3 times 3 is just 9. So I'm going to make this 9 root 24. And I'll deal with that later. And then let's take a look at this guy. I've got negative 2 times root 6 times 2. So what can I multiply here? I could multiply the negative 2 times the 2. And then just leave the root 6 alone. Negative 2 times 2 is just negative 4. And then I also have to times it by the root of 6. So I'll deal with that later. How about this next guy? Okay, we've seen this now a few times. So let's take some shortcuts here. I know I can multiply the negative 2 times the 3. And I know I can multiply the root 6 times the root 24. So can we do this all in one step now? Let's do negative 2 times 3. That's just going to make negative 6. Times the square root of, what is the root of 6 times the root of 24? Well, that's going to be the root of 6 times 24, which is just the root of 144. So we skipped a step there. Hopefully you're able to do this now that we practiced so much. All right, the hard part's done. Let's finish this off. So let's make sure that we've got everything simplified. So we have 6 here. Is there a perfect square that goes into 24? Well, 4 goes into 24, so definitely. So let's break this 24 up into 9 times the root of 4 times 6. And how about this root 6? Are there any perfect squares in 6? Well, the only factors of 6 are 1 and 6, 2 and 3, and none of those are perfect squares. So let's just leave this the root of 6 minus 6. How about a perfect square that's within 144? Well, isn't 144 a perfect square? Don't we know the square root of 144? Yes, it's just 12. So let's replace this with just 12. All right, let's finish this off. So we have 6 plus 9. And then can we skip a step here? So we know we're going to break this up into the root of the root of 4 times the root of 6. What is the root of 4? It's just 2. And what is the root of 6? It's root 6 minus 4 root 6, and then we have negative 6 times 12, which is negative 72. Let's keep going. We're almost simplified. We got 6 plus, what's 9 times 2? That's 18. Root 6 minus 4 root 6 minus 72. Okay, so there are no more radicals to simplify here. But the question is, can we just use our knowledge of algebra to simplify this anymore? Are there any numbers here that we could add together? Hopefully you're seeing this 6 plus negative 72. We can definitely add those guys together. 6 minus 72. We know that that's just going to be negative 66. How about these root 6's here? They seem to match. This says that there are positive 18 root 6's. And then we have minus 4 root 6's. So you can think of this as like an x. 18x minus 4x. These root 6's match, so it's like you're counting root 6's. How many root 6's? I've got 18 root 6's, take away 4 root 6's. That would be 14 root 6's. So we can collect like terms, like we normally do with algebra, as long as those radicals completely match, just like the letters have to match when we're working with algebra. So we have our final answer. This craziness over here is the same thing as just saying negative 66 plus 14 times the root of 6. And we're done. So I've gone back to the very first page of the lesson, where I said we need to know 2 rules to simplify radicals. And we are really, really good at this rule now, the multiplication rule. An extension to the multiplication rule is the division rule. And it makes a lot of sense if you understand the multiplication rule, where if we have a radicand that is a fraction, so 2 things that are dividing within the root, then we can just break it up into the numerator, the root of the numerator, over the root of the denominator. So I'll give you an example. We can break up, can you think of 2 things that when you divide them makes 24? Well, we could do 48 divided by 2. That's the same thing as 24. So the root of 24 is the same thing as the root of 48 divided by 2. And so we can break this up into the root of 48 divided by the root of 2. And it will give me the exact same thing as the root of 24. So that's the division rule. So let's use it for the next example. So let's take a look at this guy here, and we're going to try to simplify it. So sometimes it makes sense to just simplify what we see. Is there any perfect squares within 33? There isn't. Is there any perfect squares within 3? There's lots of ways to simplify this, but I think it's easiest to actually just make this into one big radical. So this is broken up into the root of 33 over the root of 3, which means it's the same thing, according to that division rule we just talked about, as the root of 33 over 3. And the reason why I want to do that is because 33 divided by 3 is a nice number. It's just 11. So this is just the root of 11. And we are done. Another way you could have done this is if you had noticed that, I'll do it in red. So if you had noticed that you could write root 33 as the root of 3 times 11. None of those are perfect squares, but the reason why you might want to break that up into the root of 3 over the root of 11 is because there's a root 3 right underneath. So if I were to change this into the root of 3 times the root of 11, all over the root of 3, root 3 divided by root 3, that will cancel out. and we're just left with the root of 11. So there's lots of ways to do each of these problems. So you pick the one that, which way your brain works. In this case, I think maybe it's easiest to just make this into an entire radical, just like this guy, because 33 divided by 3 is a nice number. Also, I know I'm done because there's no perfect squares in 11. So let's try the next one. All right, so we have to simplify this guy. In this case, they give it to us as an entire radical. Not so helpful as the previous one, because 3 divided by 16 is not a nice number that I want to deal with. So I think in this case, it makes more sense to break this guy up into individual roots. So break this up into the root of 3 over the root of 16. So we're using that division rule again. So the root of 3, there's not a lot I can do with that guy. But the root of 16, well, that's just 4. That's a perfect square. So I can just rewrite this as the root of 3 all over 4. And back to the very first example we did, there was that checklist on the page 2. Here it is. So remember what it said about fractions. The radicand, so what's underneath the root, shouldn't contain a fraction, but no radical should appear in the denominator of the fraction. So we got to be careful of that. So knowing that checklist, we have a radical at the top of a fraction, but not in the numerator, but not in the denominator, so we are totally fine. If we had one in the denominator, we do something called rationalizing the denominator, and that's what we're going to do in a different lesson. All right, let's try this last example with division. And so you know everything you need to know. There's nothing else for me to teach you. So you can totally do these on your own. So if you feel confident and comfortable, try it on your own. Just come back to the video once you think you've got it. If you are still super stuck and you really need me, then stay with me. But we just have 12 times the root of 75 all over 4 times the root of 3. So we can almost think of this as like a fraction, 2 fractions. This is like 12 over 4 times root of 75 over root of 3. So I can just deal with this 12 over 4 as a fraction. What would you change 12 over 4 to? Well, you just change it into 3. And then it makes sense to, because 75 is 75 is divisible by 3. It makes sense to change this guy into one big radical of 75 over 3. So we're using that division rule again. So we would change this into 3 times the root of 75 divided by 3 is just 25. And look how nicely this works out, because we know how to find the root of 25. That is just 5. So this is just 3 times 5. This is just 15. Can you believe it? This crazy looking thing, 12 times the root of 75 divided by 4 times the root of 3 is just the same thing as 15. We're done. Okay, I mentioned you can do absolutely everything without me. You don't need anything. All we need is the multiplication rule and the division rule, and you know how that works now, so you can do any of these examples that come up next. I'm just going to throw at you some weird looking ones and see if you can figure it out. So can we try to simplify this weird looking guy here? So we have 6 minus root of 45 all over 3. What the heck would we do with that? Maybe you're thinking, I want to change this root 45 into something nice. I love that idea. Or something simplified. Great idea. I'm thinking I'm going to do that, but I don't like, I see the 6 divided by 3. I know that that's going to be something really nice. That's just going to be 2. So I'm thinking that this thing divided by 3 is the same thing as 6 divided by 3 minus root of 45 divided by 3. So I'm just going to take everything and divide it by 3. And let's just see if something beautiful happens. So I'll take that minus the root of 45 divided by 3. So I know 6 divided by 3 is just 2. Minus, can we change the root of 45 into anything nice? Well, the root of 45 is the same thing as the root of 9 times 5. And then we'll divide that by 3. Will something nice happen here? So we have 2 minus, can we skip some steps now that we know this really well? This is going to be the same thing. Root of 9 times 5 is the same thing as root of 9 times the root of 5. What is the square root of 9? Can we just go right to that answer? It's just going to be 3. And what's the square root of 5? It's just going to be root 5. Nothing, we can't simplify that anymore. We've got all over 3, and look how nice. Oh my gosh. We got negative 3 divided by 3. That's just going to leave us with negative 1. So we have 2 minus 1 root 5. And we're done. All right, so you should be able to do this totally on your own now. So try doing it on your own and come back to the video once you're done. If you're coming back to the video, you should just be checking your answer. So maybe you immediately started simplifying this guy, and that's absolutely fine. Maybe you saw, well, this 10 divided by 2, that's so nice, it's going to make 5. So maybe you did what I did, which is take everything here and just divide it by 2. And then maybe you started breaking up the root. So we know 10 divided by 2 is 5. So I broke it up into 16 and 2. There's other perfect squares that go into 32. You could have broken this up into 4 and 8. But if you had broken it up into 4 and 8, let me just show you what would have happened. Nothing wrong. You would have broken it up into 4 times 8. And then the square root of 4 is 2 times the root of 8. But you can break up this root 8 again into 4 and 2. And so you'd have to go again into 4 times 2. And then that would give you 2 times 2 root 2. And that would give you 4 root 2. So you can see this is much longer than here. So you're always looking for the biggest perfect square. We're dealing with perfect squares because we've got a square root here. But we're looking for the biggest perfect square. And the biggest perfect square is 16. If you find a smaller one, no big deal. You'll still get to the same answer in the end. And so once we're left here, we got negative 4 times root 2 all divided by 2. So we got negative 4 divided by root 2. Sorry, negative 4 divided by 2 is just negative 2 root 2. And we are done. We have made it to the final examples. So I repeat, I have taught you everything we need to know. I taught you everything we need to know like 15 minutes ago, 20 minutes ago. So now we're just applying the division rule, the multiplication rule, and just seeing what you can do with it. So how about with some adding and subtracting? We did some adding and subtracting in a previous example, but all you really need to remember is this guy. The radicand can be treated like a variable. You can add or subtract like radicands, just like you would add or subtract like terms. So if I have, for example, if I have 2 root 3's, and then you have plus another 5 root 3's, you're just counting the root 3's. That means there are 8 root 3's. But if I have 3 root 3's and 5 root 2's, like there's nothing else I can do. I still just have 3 root 3's and 5 root 2's, so we're done. We can't add root 3's and root 2's together because we're not counting them, just like variables. So let's try these guys. Can we just count how many root 3's we have? We have 4 root 3's here, plus another 2 root 3's, minus, we know that that's just a 1. So we got minus 1 root 3. How many root 3's are there? 4 plus 2 is 6, minus 1 is 5. So we have 5 root 3's. And this is as simplified as it possibly can because the only factors of 3 are 1 and 3, and neither of those are perfect squares, so we're done. Let's make it slightly harder now. Let's try this guy. What can we add together here? First of all, check and make sure these roots are all simplified. 5, no perfect squares in 5. 7, no perfect squares in 7. So let's take a look. Are there any ones we can just add and subtract together? Well, we can count the root 5's. We have 8 root 5's here, minus another 4 root 5's. And then we have the root 7's. We can take negative 3 root 7 plus another 7 root 7's. So how many root 5's do we have? So we've got 8 root 5's minus 4 root 5's. That's going to be just 4 root 5's. And then how about counting the root 7's? We've got negative 3 root 7's plus another 7 root 7's. Negative 3 plus 7 is just going to be positive 4 root 7. And we can't add root 5's and root 7's together, so we're done. Let's try this last example. So it's all adding. We got 7 root 12 plus root 18 minus root 27 plus root of 50. And just at a glance, it looks like we're done, right? Because none of these are like terms. But maybe there are like terms hidden inside these, and we just have to simplify these roots. So can we simplify the root of 12? Are there any perfect squares hidden in there? Well, there is, because 12 is divisible by 4. So we can change this into 4 times 3, root of 12. How about in root of 18? Are there any perfect squares hidden in there? Well, the first number I think of is 9. I can change root 18 into the root of 9 times the root of 2. And how about 27? There's another 9 hidden in 27, so we can change 27 into 9 times 3. That's a times, not a minus. A times. Okay, that's just an awful dot now, but that's a dot. And then let's change this root 50. What's a perfect square that goes into root of 50? Well, we could change this into the root of 25 times 2. So let's keep simplifying and see if something magical can happen. So I'm going to change this 7 times, is the same thing as 7. This root 4, that's just going to be the same thing as 2. So I'm just going to change this to 2. And then root 3, I'm just going to leave as root 3. Can't get more simple than root 3. And then plus, we got the root of 9. What the heck is the square root of 9? That's just 3 times the root of 2. Can't do anything about the root of 2, so I'm going to leave it alone. How about the next guy? I got negative, again, root 9. Root 9 is just 3. So square root of 9 is just 3, and then times the root of 3. Root of 3, here we go. And then plus, what the heck is the root of 25? It's just 5. So we got plus square root of 5, square root of 25 is just 5. Then we have times the root of 2. Okay, anything beautiful happening here? Let's simplify this 14 here. So we got 14 root 3 plus 3 root 2 minus 3 root 3 plus 5 root 2. So at first this question looked like we were done at the beginning because no common or like terms. But now that we've simplified each of these radicals, we can see that there are like terms here. There's 14 root 3's here, minus another 3 root 3's here. So we can definitely simplify that. And then also the root 2's. I've got 3 root 2's here plus another 5 root 2's. Let's simplify these. How many root 3's do I have? I've got 14 minus 3, so it's 11 root 3's. And then how many root 2's do I have? I've got 3 plus 5 root 2's. That's going to be 8 root 2's. And these guys aren't like terms, so we are done.